They seem eternal, silent, and unchanging. But stars are born, they live, and they die in ways we are only beginning to understand. To us, looking up from Earth, the stars look like fixed, eternal points of light in a silent sky. But look closer, beyond the limits of human time, and you'll find a violent cycle of birth and destruction that spans billions of years. Colossal clouds of cold gas collapse under their own weight, igniting into brilliant, roaring fusion engines. A star is not a permanent fixture. It is a temporary, fragile balance between crushing gravity and explosive nuclear fire. And eventually, that balance breaks. It begins here, in the cold, silent depths of a stellar nebula. These molecular clouds are the grand nurseries of the universe. Stretching across dozens of light years, they contain enough raw material to build thousands of solar systems. Their composition is elegantly simple, mostly primordial hydrogen gas, mixed with traces of cosmic dust. Suspended in temperatures near absolute zero, this delicate structure waits in perfect stillness until a cosmic spark begins the collapse. A nearby shockwave, perhaps from the violent death of a neighboring star, disturbs the cold molecular cloud. This shockwave compresses the gas, pushing it past a critical threshold. Gravity takes absolute hold. Pieces of the nebula begin to free-fall inward, accelerating toward a common center. As this massive cloud collapses, gravitational potential energy is violently converted into heat. The gas clumps together, atoms colliding faster and more violently, causing the core temperature to skyrocket. Energy that was spread across light years is being ruthlessly crushed into a tiny, intensely hot space. This glowing, spinning disk is a protostar, a crucial stepping stone in the stellar life cycle. Right now it's glowing intensely, but not from nuclear fusion. The light you see comes entirely from the sheer friction of falling gas crashing into the core. It hasn't quite ignited yet. This cosmic pressure cooker is constantly heating up as more material rains down. To become a true star, the core must reach a staggering 15 million degrees Celsius. Only then can the real magic begin. Deep within the core, temperatures exceed 15 million degrees. Under this crushing pressure, the natural repulsion between atoms is overcome. 4 hydrogen atoms are violently forced together, merging to create a single helium atom. But the new helium atom weighs slightly less than the 4 original hydrogens. That tiny amount of missing mass doesn't just vanish, it is converted entirely into pure, radiant energy. This is nuclear fusion. The star has finally ignited. It has entered the main sequence, the longest and most stable phase of its life, where it will burn steadily for billions of years. For billions of years, a main sequence star exists in a relentless, delicate tug-of-war. On one side is gravity, an immense inward force constantly trying to crush the star into its center. On the other side is the outward thermal pressure generated by nuclear fusion in the core, which wants to blow the star apart. As long as these two opposing forces remain perfectly equal, the star achieves a state called hydrostatic equilibrium. This perfect balance maintains a stable size and is the exact stage our Sun is in right now. For billions of years, a star burns steadily on the main sequence. But eventually, the hydrogen fuel runs out. This is the ultimate moment of truth. The path a star takes from here depends entirely on one factor, its mass. The universe splits stellar evolution into 2 distinct destinies, massive giants and average stars. Let's follow path 1 first, the journey of an average star, like our Sun, with no more hydrogen in the core. The delicate balance of hydrostatic equilibrium breaks. Without the outward pressure of fusion, gravity takes over. The core collapses inward, becoming incredibly dense and hot. But this intense core heat triggers a new reaction, causing the outer layers to puff out aggressively. The star swells to hundreds of times its original size, transforming into a red giant. Although its surface cools and turns a deep crimson, it becomes massive enough to completely swallow the inner planets orbiting it. The outer layers eventually drift away into space, creating a beautiful glowing shell known as a planetary nebula. This is the gentle death of an average star. What is left behind is the exposed, searingly hot core, a white dwarf. It is incredibly small, about the size of Earth, but unimaginably dense. A single teaspoon of its material would weigh as much as an elephant. With no fusion left, this stellar ghost cools over trillions of years, fading to a cold black sphere at the edge of time. But what about stars that are born massive, at least 8 times the mass of our Sun? For these cosmic giants, the evolution is far more extreme. They swell into colossal red supergiants. Unlike average stars, their fusion engine doesn't stop at helium. The crushing internal pressure forces heavier elements to ignite. They fuse carbon, then neon, then oxygen, and silicon, building up internal layers like a massive cosmic onion. The heaviest elements sink to the center, while the outer surface boils with violent, turbulent energy. Inside the supergiant, a desperate race against gravity creates an onion-like structure of fusing elements. Hydrogen fuses into helium, then carbon, oxygen, and silicon. But this elemental factory hits an impenetrable wall, iron. The process stops at iron. Fusing iron doesn't release energy, it consumes it. Without outward thermal pressure, the star's delicate support system is shattered. Gravity wins instantly. In less than a single second, an iron core the size of Earth collapses under its own weight, shrinking to the size of a city. The outer layers lose their support, plummeting inward and slamming into the ultra-dense core, resulting in a supernova. The core's rebound triggers a shockwave of unimaginable power, tearing the star apart from the inside out. For a few brief weeks, this single dying star will outshine its entire galaxy, releasing more energy than our Sun will produce in its entire lifetime. This is the most violent explosion in the cosmos. Yet, within this chaos lies the ultimate act of creation. The extreme temperatures and pressures of the supernova forge the heaviest elements on the periodic table. Precious elements like gold, silver, and uranium, which cannot be made during normal fusion, are created in these fleeting milliseconds. Finally, the explosion acts as a cosmic cannon, blasting these newly forged materials across the universe, seeding the dark void with the building blocks of future worlds. When the supernova clears, the core's fate depends on its mass. If the core is heavy, it becomes a neutron star. The gravitational crush is so intense that atoms are shattered, crushed into pure neutrons. The result is a sphere the size of a city, spinning rapidly and emitting intense beams of radiation. But if the core is even more massive, gravity wins completely. No physical force can halt the collapse. It crushes inward to a point of infinite density, creating a black hole. Its gravity becomes so extreme that it warps the fabric of space and time itself, forming an event horizon, a boundary of absolute darkness where even light cannot escape. To truly understand this cosmic scale, let's step back. Imagine our entire planet Earth as a single grain of sand. On this scale, our Sun, a typical main sequence star, would be roughly the size of a basketball, sitting about 100 feet away. It's massive to us, containing over 99% of our solar system's mass. But in the wider universe, it's just average. Now compare it to a red supergiant like Scuti. If the Sun is a basketball, this dying giant would be larger than the Empire State Building. It is so unimaginably vast that if placed at the center of our solar system, its surface would swallow Jupiter. The sheer variety of stars is as vast as the space they inhabit. This cycle isn't just a cosmic light show, it is the fundamental factory of the universe. In the beginning, the Big Bang gave us only hydrogen and helium. Everything else had to be manufactured. Every atom of oxygen you breathe was fused in the crushing core of a massive star. The carbon that forms the backbone of your DNA was created in the dying embers of sun-like stars. And the iron rushing through your blood was forged in the final desperate moments before a supernova explosion. Without the violent death of stars, the universe would be a lifeless void. We are made of star stuff. Look at your hand, the atoms in your skin, the calcium in your bones, the iron in your blood. None of it originated on Earth. They were once part of a vast cloud of gas, billions of miles away. Over eons, they were drawn together, crushed in the fiery core of a massive star, and forged under immense pressure. Then, they were violently blasted across space in a supernova explosion. Eventually, these wandering elements gathered to form our world, and ultimately, you. You are, quite literally, made of stardust, a living piece of the cosmos. The death of one star is not an end, but the spectacular birth of the next. The heavy elements released by a supernova, iron, carbon, oxygen, drift across the cosmos, eventually mixing with pristine clouds of hydrogen. Over millions of years, these enriched remnants condense, paving the way for a new generation of stars, rocky planets, and perhaps new life. In the vast machinery of the universe, nothing is ever truly lost. It is only transformed, beginning the eternal cycle once more.